In this video, we're going to talk about a problem that's inspired by the O'Reilly Auto Parts supply chain or distribution channels. Specifically, we're going to look at the Southeast United States here. And these gray dots here that you're seeing are locations of stores. And so what I did, that's actually been a couple of years ago, but I was able to write some code to scrape the O'Reilly corporate website and identify the locations of stores and the location of distribution centers. So the little gray dots here represent stores in the southeast part of the United States, and the bigger blue dots at this point represent stores, but now we're going to assume that these stores have been affected by snowfall. So it's kind of the southeast part of the United States, the lower end of the Appalachian Mountains there. And so a little bit unusual, but let's say there was a heavy snowstorm in this area that caused a certain demand to show up with certain products in this region. And so what you're seeing here is a simulated snowstorm where I'm saying something like around 10 inches gets hit here in the upper parts of Georgia, Alabama, and the lower southeast part of Tennessee there. And so with this snowfall, basically we're going to say that there are a set of products that you can see in this drop down on the left that have an increased level of demand. And so for instance, if I change to this Prestone windshield deicer, I'm seeing a total demand of 12,600 units. And if I hover over the yellow dots now, for instance here at the Chattanooga, Tennessee store, labeled number 1032. You can see the address there and the latitude and longitude. We're saying there's a demand of 84 units of this deicer there. And so, similarly, I've got this for other products as well. So I can just kind of shift through the products, and you can see the yellow dots will change a little bit here. So that's going to be the demand side of things for our supply chain type problem here. And then on the supply side, you'll notice that there are some red dots here. The red dots represent locations of distribution centers. And so in this case, there are 6 of them that we're going to consider. One in Saraland, Alabama, another one in Horling, Mississippi, Lebanon, Tennessee, Forest Park, Georgia, Greensboro, North Carolina, and Lakeland, Florida. And we're going to assume that each one of these distribution centers has some amount of the product. So in this case, I've currently got selected some sort of de-icer and ice melt, and there's a total of 8,980 units that are stored across these 6 different distribution centers, and you can see the amount per distribution center here also in this grid. And so there's the supply side of things. Now, the overall problem here is we need to basically be able to move these products from the supply nodes, aka the distribution centers, to the demand nodes, aka the stores. But it costs a certain amount to move the products around, and so that's what this lower left-hand table is going to simulate. And so what I've done is I've basically found a correlation, if you will, between the distance between a distribution center to a store, and then I basically use that as a relationship in order to come up with some fictitious unit cost of shipping a product. So for instance, for this de-icer and ice melt, if I was to take it from the Forest, Georgia distribution center to the store number 1016 in Knoxville, Tennessee, we're going to say for every unit it takes to move between those 2 sites, it's going to cost us roughly 20 cents there. And so there's the cost side of things. And this brings up an interesting problem, because now the problem is going to be, how do I satisfy the demand of the stores by using the supply at the distribution centers, but also do it at a minimum total shipping cost? Because there's obviously a lot of combinations here, just between how many cities that, for instance, Horn Lake, Mississippi services versus Lebanon, Tennessee, and not just how many, but also which ones are they going to service. And for every store they have, are they going to supply the entire amount there, or are they going to split it across multiple distribution centers as well? Now, this problem we can think about in the terms of linear programming as the transportation problem, and that's what we'll, in this video, model out for us. And so, as I transition from this Plotly dash web application, we'll now just move over to Excalibur, and we'll actually write out the mathematical model here. And then in a follow-on video, we'll actually go through and solve it using the very similar tools that the web application is going to be using. So transportation problems are interesting problems from the world of operations research, because you can illustrate them all as graphs. And so that's what you're seeing here on the screen. when I say graph, do not think of like a chart in terms of a bar chart, a pie chart, something like that, but instead think of a mathematical graph. This is in graph theories where we talk about nodes and edges. And so in this case, in the green on the left-hand side, I've got a series of nodes. These are my supply nodes, also known as the distribution centers, and I've went ahead and just labeled each one by the city. Then on the right-hand side, if I was to write all of them out, you would have all the retail stores. And so here I just wrote 3 and then put the ellipses and you get the idea. So here I've got demand side of things. And then at this point, the edges or the arrows connecting them talk about the different options with respect to shipping. So for instance, I could take units from Saraland, Alabama, and I could send it to Calhoun, Georgia, Athens, Tennessee, Murphy, North Carolina, so on and so forth there. And one thing I'm not showing here with respect to these edges in the middle is think of them all as weighted edges. So I would typically write here, assign a weight to the edge connecting Saraland, Alabama to Calhoun, Georgia, and that weight would be this unit cost that we would find in this table. So that we would then know for every unit of a certain product that I'm moving from Saraland, Alabama to Calhoun, Georgia, I would be considering the cost of moving it by that weight of that edge. Another thing that I'm leaving off on this is we would just acknowledge the fact that for any given product, we would have a certain amount of supply at each one of the distribution nodes and a certain amount of demand at the retail nodes. So this picture will help us a little bit in terms of writing out the mathematical model. So I'll just slide over here and we will start on writing out the model that is driving this web application. So when I write this model out, a lot of times I think about the Pyomo algebraic modeling language that I'm going to use later to actually model it out and then throw it to a solver. And so when you start thinking about those models that you write in Pyomo, one of the first things you typically want to think about are sets. And so I will first write out some sets. Oops. Give me one moment to get the right tool in place. All right. And so in this case, we can have a few different sets to worry about. One thing we have are distribution centers. And so we need a set to include those. And so I'll just generalize this at this point. And instead of labeling each one, we'll just call it D1, D2, D3. And these are our distribution centers. Following the distribution centers, we have on the other side of our network some stores. So I'll just say that's S1, S2, some S3, and on we go. And then finally, we have some products. Notice I think we had between 5 or 6 different products there that we were considering. All right, so now that we have our sets, we next need to think about some parameters. Now, the parameters are the input pieces of data that we would have to worry about when constructing the model. So if I look over here, a lot of this input data is right here in the far left side of the problem overview tab. And so the first thing that I'm seeing here is I have a certain amount of inventory of a given product at a given distribution center. So for instance here, if I hover right here, that row represents the amount of this de-icer and ice melt stored at Lebanon, Tennessee, and the value would be 1800. So we need a way to include that in our model. So I'm just going to first off start with a variable letter A for this parameter. And then we need to have some subscripts for this. And so when I was talking about it over here, Notice we have two different things to describe here. One is the product, and the other is the distribution center. And so those are two of our sets, a product and a distribution center. I'll start with the distribution center first, so I'll say it's subscript by D and P. We'll also say it is an element of the set of integers. And we'll need one of these values for every distribution center in the set of distribution centers, as well as for every product in the set of products. So again, just to talk through the mathematical notation, I've got some variable a, d, comma, p. So this is the parameter that is indexed on the set of distribution centers and the set of products. This symbol here is an element of, so an element of the scripted z is the set of integers. And then this right here is basically saying the upside down is for all, or so for every d, which is inside the set of distribution centers d, and for every p, an element of p, so that's for every product in the set of products here. And then in blue, we'll just talk about this. This is the inventory of product P at distribution center D. Okay, so now that we have that in place, we go to the other side of the supply chain and look at the stores. And so as I'm hovering here, you can see there are certain demands on the stores, right? Again, we're talking about a de-icer and a knife smelt. And so for instance, this store number 1359 out of Boaz, Alabama needs 89 units there. And so we need a way to describe that to the model. So we used A for our first parameter. Let's just use B for this parameter. So I'll say B of, what are the subscripts is the next question? Well, B of what? Well, in this case, I have to talk about a store, right? And I also have to talk about a product. So again, two subscripts here. Let's start with the store first. S comma P. Again, we'll say it's an element of the integers. And we'll say we need to write one of these parameters for every S in the set of S, so for every store in the set of stores, and for every P, which is an element of P, so for every product in the set of products. And so this represents the demand of products P at some store S. All right, so at this point, we've talked about this input data. We've talked about the input data shown by these yellow circles. The other thing we need to talk about is this in the bottom left. This is the unit shipping cost. These were the weights associated with these edges on our graph. And so we think about this. Let's use some variable C. I like C because it is a cost, and C starts with cost. Or cost starts with C, excuse me. And so here we actually need three subscripts. The three subscripts I'm thinking about is I have to describe a distribution center, and then I end at some store S, so there's two subscripts there, but I also need to talk about a certain product P. So a total of three different subscripts in this one. So we will write that as C sub D, S, and P. And this one, it does make sense that we would be able to say that is an element of the reals instead of the integers. Obviously, the values that I'm showing here are not integers, but instead of real numbers. All right, so now we need to write one of these for every combination that we have. So that'd be for every D in the set of distribution centers, for every store in the set of stores, and for every product in the set of products. So this here, make sure it doesn't get confused with that one, is the unit shipping cost to move product P from some distribution center D to store S. All right. So we're doing fairly well at this point. We've been able to define our sets. We've been able to define all the input data that you're seeing on this problem overview tab. And now we can move on to our variables. Now these variables in the world of linear programming are the controllable inputs that you have at your disposal. And so what would be the controllable inputs that we have here? What are the decisions we need to make? Well, the overall decision we need to make is we need to be able to say to someone, take so many bags of this de-icer and ice melt from a distribution center like Horn Lake and send it to some store, such as store number 1364 out of Dunlap, Tennessee. And we have to make a lot of these decisions, right? Because we have 6 different distribution centers, and it looks like we have quite a few stores. This is where it's helpful to use linear programming to kind of mechanize this type of decision-making process, as well as pursue optimality. And so for a decision variable here, I will use the letter X. And again, we need to think about subscripts. And in this case, again, we have all 3, because I need to remember, say I'm going to move a certain product, there's the P, from a distribution center, D, to a store, S. So in this case, we have X, so D, S, and P. And so what is this an element of as far as what type of value is this? Well, in reality, this is probably going to be an integer. But if you'll let us call this now a real number. Um, Reasoning being because of the inner workings of the solvers that is going to be solving this model itself. Just the algorithm has to be different between ones that consider decision variables as real and continuous versus ones that are integer based there. Also, for this specific problem that we're working on, the transportation problem, just because of the fact that I have the demand as integers, the supply is also integers there, and the overall format of the way this problem is, some properties of it from the mathematical structure. Even though I'm going to specify that these variables are elements of the reals, what we'll find out is that they're actually going to be integer values at the end anyway, which is very nice for this specific problem. All right, so with that being said, let's write the rest of this formally to say this variable, I need one for every distribution center, every store combination, and every product combination as well. And again, just to write this out in words, this is the quantity of product P to ship from a distribution center D to a retail store S. All right. Doing well so far. And now we can work into what looks like the real more traditional part of the model, I guess, if you will. This is kind of just the preliminary work to define the things that are going to go into the model. And so the first part of the linear model that we're needing to think about is the objective function, and specifically the sense of the objective function. Now, the objective function typically is a maximization or a minimization. Here we are talking about cost and wanting to reduce the cost as much as possible. So it makes sense that we're going to be talking about a minimization problem. So we're going to minimize the objective function. Now, what is the objective function is the next question. Well, the objective function for this is going to be a expression that computes the total shipping cost of moving all the products from the distribution centers to the stores. And the way we're going to do this is through an actual 3-nested sum description. And so what I'll do here is I'll go ahead and write the summations out here. And then we have three sets, so we'll write those in here. And so by doing these three here, we're going to basically grab all the combinations that we could possibly have between the distribution centers, the stores, and the products. Now, what exactly are we summing? Well, we're going to be summing a product. We're first going to have to consider my decision variables. And this is talking about how many of some product that I'm moving again from a distribution center to a store. And I'm multiplying that now by the unit cost here. Excuse a little bit here. I can write that just a little better for us. There. And so hopefully this makes sense as far as we now have something that talks about the number of units that I'm moving times the cost to move per unit. So that should be the total cost to move for that given action. And then we're going to sum that up over all the possible actions, which allows this to become the total shipping cost. So we would consider that first line here to be the objective function. Here's the sense of it. And then we separate it typically in the realm of linear programming with something like ST. And we're separating it here from our constraints that we'll write down below. And so the next thing to think about are the constraints. Well, in the transportation problem, there's really two different types of constraints that we're going to be thinking of. One is associated with the inventory at the distribution center, and one is going to be associated with the demand that we're seeing at the stores itself. So let's start with the stores. So we need a constraint or a series of constraints that ensure that the demand is met for every one of these stores. And the way I typically think about writing these is a little bit backwards from the typical English way of writing. Usually we write left to right, but this time I'm going to write right to left. And so one of the things I'm thinking about is I have to satisfy the store, or satisfy the demand of every store and for every product. And so I'm going to start over here and say I'm going to write something for every S. It's an element of S. So for every store and for every product as well. So I need to peek at the parameters we have here. One of the things I want to do is satisfy the demand. So the demand, it looks like we described right here. So we would say this is B of S comma P. We need to satisfy it, so we need to have something equal to it. And then we need to figure out the left-hand side of this, this equality. And so one way you can think about this is using our graph here. So say we're looking at a retail store, like this top right one with Calhoun, Georgia, and we have some products that we have in mind, and we're trying to figure out the left-hand side. So what we do is look at all the arrows coming into Calhoun, Georgia, and we see that every one of those arrows is coming from a distribution center. So the left-hand side will be something like the summation across all the distribution centers, and we're summing the decision variables because that decision variable represented the movement of products from a distribution center to a retail store. So to write that out down here, we would say again, I'm summing across all the distribution centers. And I am summing the decision variables. And that would be our constraint. So this constraint is to be a description of satisfying store demand. It's important to also note here, although I wrote that as a single line, this is actually going to be many different constraints, right? Because I have to write a constraint for every store and for every product. All right, so we've at this point taken care of the demand at each store. Now we need to take care of the inventory at the distribution centers. And by take care of, I basically need to write rules such that the inventory is not exceeded. We can't go negative here. These values can only go down to 0. Another way of saying it is, for instance, for this product at Forest Park, Georgia, I can only have 1,690 leave Forest Park, Georgia because that's all I have in the distribution center. So similarly to our first constraint here, I'm going to work my way from the right side to the left. First, I have to acknowledge the fact that I need to write one of these constraints for every distribution center as well as every product as well. And so we would say now for every D, which is element of capital D, so every distribution center in the set of distribution centers, and for every P, which is an element of P, so for every product in the set of products. We need to set some sort of upper bound at this point associated with what can leave the distribution center. So we have that upper bound being this inventory parameter A. So that'll be on the right-hand side. And we talk about this as an upper bound. So we don't necessarily need inequality, but instead we can say this is a less than or equal to. Again, establishing the upper bound here. And then on the right-hand or the left-hand side, we can again consult our graph here. So if I pick a distribution center and assume I'm talking about a single product, I now need to basically consider everything that's leaving the distribution center. So again, we look at the edges on the graph, or these arrows, if you will. And so we can see here that the total amount of things that are going to leave Saraland, Alabama for a given product will be the sum of what goes to all the different retail stores. So noticing that, I will make a summation across now the stores. And what I'll be summing are the decision variables. And so again, this line here represents the inventory limits at my distribution centers. And again, although I've written that as one single line, there's going to be many different actual constraints that are going to come out of this, right? Because I'm having to write it for every distribution center and every product. So those are the big constraints that I can think of for this transportation problem. The other thing that I would suggest writing to be very explicit is the non-negativity constraint. So we would write something like x of d, s, p must be greater than or equal to 0 for every d is an element of d, for every s an element of s, and for every p which is an element of p. Just to confirm that these will be non-negative decision variables. All right, so as I page out, we now have our mathematical model. It's a little small there, but hopefully we can still see it. In the end, not too awfully big, but still very powerful in and of itself. So as I transition from this mathematical model, I'll come back to my PolyDash app, and basically what this app has now is a formulation of this model that I can then solve. We're basically formulating again this model with the Pyomo algebraic modeling language, and we're going to pass it to the GNU linear programming kit, or the GNU solver. I can do runs model here, and that gets us to the solution tab. You can see here that the objective function returns a minimal cost of $7,184.48. The map is showing all the different shipping lanes that are happening. Right now, our product selection is on all, but if I go to an individual product like this deicer, here you're going to see the actual plan down here as far as to move a certain amount of this product from a certain distribution center to a certain store, and then also shows the effects of the distribution center usage here. So for in this case, we use up all of the inventory at every distribution center except for Lakeland, Florida, which we leave roughly 3.5% there. Not too surprising there because we see a correlation between the cost to ship products and the distance, and Lakeland, Florida seems to be the farthest away from the affected stores from that simulated snowfall. Another interesting point to make here, as we can look right here, is that since Lakeland, Florida is the farthest away, intuitively you would almost expect it to always just hit the nearest possible stores. But notice here there are some traces that are green that go relatively far north, right? For instance, this one goes all the way up to Knoxville, Tennessee. Knoxville, Tennessee also looks like it may be an interesting case as well. So I'm going to filter my plan. Knoxville, 1016. There we go. Notice here, Knoxville, Tennessee, store number 1016. You can see by the lines here, the green and the purple both coming to this node, that the total 59 units received is actually split across two different distribution centers, one in Lakeland, Florida, and one in Greensboro, North Carolina. There, 34 and 25. And so this may or may not be something that we want to achieve as far as we could potentially expand on this model a little bit and say, well, for any given store, we only want one distribution to service it potentially. That would be a slightly different model that we would have to solve, but we could potentially consider that for a follow-on video. It looks like Knoxville, Tennessee is not the only one. As I zoom out here, it looks like this other place, Ooltewah, Tennessee, store 956, potentially also has two that are coming together. One from, it looks like, Atlanta, Georgia, and the other one coming from Saraland, Alabama. One of the nice things that we just saw, though, with the solver is that it solved almost instantaneously, and with linear programming we are guaranteed this is the lowest cost solution given the definition of the objective function as well as those constraints. And so thank you for watching the video. Thank you for making it to the end. Hopefully you've enjoyed this. Hopefully this has made the illustration of the transportation problem a little clearer and also shows the value that it can have for these type of supply chains decisions there.